Welcome! Let's take a look at an example of finding the open intervals on which a function is increasing or decreasing. We know that for a differentiable function, it will change its behavior from increasing to decreasing or vice versa at the critical points of the function. So let's go ahead and start by finding the critical points of the function. So critical points come from two sources. One source of critical points is where f prime of x equals 0. The other source of critical points is where the f prime of x is undefined, or where it does not exist. So let's go ahead and find our derivative. The derivative of this function is f prime of x is equal to 3x squared minus 6 times 2x. Or we could simply say f prime of x is equal to 3x squared minus 12x. So looking at our first source of critical points, we're looking at solving the equation 3x squared minus 12x equals 0. Now to solve that equation, we can factor. Let's factor out a 3x, leaving us with an x minus 4 factor. And then either 3x equals 0, so x equals 0, or x minus 4 equals 0, so x would have to equal 4. So from our derivative equaling 0, we have two critical points. Now let's take a look at our second source of critical points. These would be points where the derivative does not exist. Now notice our derivative is a nice quadratic, nice polynomial, and is defined for all real numbers. So f prime of x is defined for all real numbers. And so there are no critical points from this source. So no critical points. So now we need to determine the intervals on which our derivative is positive versus negative. And so we divide up our number line, our x-axis, at the critical points. So we're going to be testing f prime of x and noting whether the function is positive or negative on these various intervals. So our first critical point to the left is 0, so we will have an interval from negative infinity to 0. And then we'll move to the next interval, which is 0 to 4. And then we'll have a third interval that starts to the right of 4 and extends on towards positive infinity. And so what we want to know in these various intervals is whether the function is positive or negative there. And to determine that, I simply need to choose a value of x in that interval and determine whether or not it's positive or negative. So let's first take a look at the interval from negative infinity to 0. Negative 1 is a nice number, so let's see what f prime at negative 1 is. That's going to be 3 times negative 1 squared, so that's a positive 3, minus 12 times negative 1. And really, we're not interested in that value, we're just interested in the sign. So I have a positive 3, and this is going to end up being plus 12. So this is going to be a positive value, which means that in the interval from negative infinity to 0, my derivative will be positive. Let's choose a value to represent the interval from 0 to 4. Again, choose values that are easy to work with. So let's try f prime at 1. We'll have 3 times 1 squared, so that's a nice positive number, minus 12 times 1. Now notice this time this second term is not going to become positive. And this second term is larger in magnitude. So when I do this subtraction, I'm actually going to end up with a negative number. So the derivative is negative in this interval from 0 to 4. Now let's choose a representative number from the interval from 4 to infinity. 5 is a nice number. So let's check f prime at 5. We will have 3 times 5 squared minus 12 times 5. So 5 squared is 25, and 3 times 25 is 75. So I've got 75 minus 60. So 75 is bigger than 60. So this is going to be a positive value. So we know that on the interval from 4 to infinity, our derivative is positive. Now keep in mind that on the intervals where the derivative is positive, my function is increasing. So from negative infinity to 0, and then from 4 to infinity. And then on intervals where my derivative is negative, my function is decreasing. So we would say that our function is increasing on the interval from negative infinity to 0, union the interval from 4 to positive infinity. And that our function is decreasing on the interval from 0 to 4. So now that we know where our function is increasing versus decreasing, let's go ahead and apply the first derivative test to find the relative extrema of the function. Now remember, our critical points are at x equals 0 and x equals 4. So we want to look at the behavior to the left of each critical point and to the right. So we see that to the left of x equals 0, our derivative is positive, or our function is increasing. And to the right of 0, our derivative is negative, or our function is decreasing. Now, x equals 0 is one of our critical points, and so as the function goes from x equals 0, from increasing to decreasing, we will have a relative maximum at x equals 0. So we can say there is a relative maximum of f at 0 at x equals 0. Well, what is f of 0? Let's go ahead and find that. So f of 0 is 0 cubed minus 6 times 0 squared, which is 0. So we're going to replace that f of 0 with its numerical value, 0. So there is a relative maximum of 0 at x equals 0. Now let's see what's going on at x equals 4. Now we can see that in the interval to the left of 4, our derivative is negative, so our function is decreasing. And to the right of x equals 4, our derivative is positive, so our function is increasing. So by the first derivative test, this means that there is a relative minimum at x equals 4. So we can say there is a relative minimum. Sometimes these are referred to as local maximums and minimums of f of 4 at x equals 4. Well, let's go ahead and figure out what that f of 4 actually is. So f of 4 is equal to 4 cubed minus 6 times 4 squared, which is negative 32. So let's go ahead and replace that f of 4 in our statement with the actual value of negative 32. So we have a relative minimum of negative 32 at x equals 4. And so to confirm the work we've done here, let's just take a quick look at the graph of this function. We anticipate seeing the function being increasing from negative infinity to 0 and from 4 on to infinity, and to be decreasing on the interval from 0 to 4. So let's take a look. So I've labeled the intervals on the x-axis on which we expected to see either the increasing or decreasing behavior. Now it can be kind of distracting to see the x-intercepts, and that can kind of confuse our understanding of what we thought we found. So I went ahead and put these vertical yellow lines at x equals 0 and at x equals 4 because we found the x equals 0 and x equals 4 to be our critical points, and what we want to do is focus on the behavior between those. So to the left of x equals 0, we can indeed see that this function is increasing as x increases. Then from the interval from 0 to 4, we can indeed see that the function is decreasing as x increases. And then here at 4, to the right, we can see that our function is indeed increasing as x increases. So we are confident on the intervals for increasing and decreasing behavior. One other thing we want to check is our relative maximum of 0 at x equals 0 and our relative minimum of negative 32 at x equals 4. So let's take a look. So looking at our graph here, we can indeed see that we do have a relative maximum at x equals 0. That maximum, or the y value, is in fact 0. We also have a relative minimum at x equals 4. That relative minimum is negative 32, or the y value that corresponds to x equals 4. So indeed there is a relative minimum of negative 32 at x equals 4. I hope you find this helpful.